Okie dokie. So this is for Becca, because Becca is in class today. She's taking her test, so hopefully she'll see this and do just great. We want to talk about graphs of polynomials. You should be able to graph any polynomial by the time we're done with this section. Almost any. There's some that are a little bit trickier, but for sure, first, second, third, fourth, fifth, those are going to be ones that we can do a pretty good job at. And if you see an x to the first, that's going to make a line. X squared makes parabola. X to the third makes kind of one of these wavy things. Okay. X to the fourth, kind of like a W. Did I hear W over there? Julian, A for the day. X to the fifth. Do you see a pattern? What is the pattern? Adding an extra wave. That's a nice way of saying it. So let's take Taylor's idea, okay, and let's formalize it in terms of what we refer to as local extrema. Local extrema are going to be the kind of the minimums and the maximums of the graph. How many minimums or maximums does this thing have total? 4. Fifth degree polynomial. 4 of them. How many does this one have? 3. Fourth degree polynomial. Third degree. So, given a polynomial has degree n, there are at most how many local extrema? N minus 1. I believe the hey what came from Carissa D. Is that correct? All right. So if you look, this has 4 extrema, mins and maxes, and it's a 5th degree. This has 3 min-maxes, 4th degree. So it's always the degree minus 1. At most, because you could have situations where they have less, but at most, that's the number. Okay, this is probably the most challenging part for people to think through, I think, just in terms of the terminology. So really try to focus this here. But we're now going to talk about something called end behavior of these functions. And we're going to look at different conditions. We're going to suggest, let's consider if the polynomial was odd, meaning the degree of the polynomial, the power was odd. So 1, 3, or 5. And the leading term was positive. And then we're going to look if n was even and the leading term was positive. Okay? This reads as follows. As x approaches or goes to negative infinity, what we want to see is as the x values go towards negative infinity, what happens to the y values? So I'm just going to look at an example here. It says n is odd and it's positive. So this one right here, 3rd degree, that's an example of where the power is odd and this is a positive polynomial. I'll draw the negative ones in red so you can see the difference. So if I march my x values out this way, okay, as I go further out this way, what happens to the y values? They drop. Everybody see that? As my x values go out here, my y values go even further down there. I mean, if I were to draw this blue line and really extend it, you can see that as x goes out this way, y drops, and it drops really quickly. So as x goes towards negative infinity, y goes towards negative infinity as well. We call that the end behavior of the graph. As x goes towards negative infinity, y goes towards negative infinity. Yep. Now let's try the next part. Let's suppose that x is going this way towards positive infinity. What happens to the y value? It goes as well towards positive infinity. let's look at another positive function, but instead of having an odd power, let's look at an even power, such as a fourth degree polynomial. Let's look this way. If x goes towards negative infinity, what happens to the y value? Up towards positive infinity. And as x goes towards positive infinity, what happens to the y value? It also goes towards positive infinity. So, look at what we have. Yes, question. Whether I'm looking at the third degree or the fourth degree. So right now, the chart that we're filling out says if the power is odd, so we use the third degree. And then this one says if the power was even, so that's when we use the fourth degree. First would be if it was odd. And if you notice, it holds true. We could do the same thing for what we did for fourth degree. We could do the same thing for second, and you'd see the same scenario. What we did for third degree, you could try for first and fifth, and we'd see the same scenario. Question? Yep, that's what we're going to do next. So I'm going to draw the negative ones in red. So if the leading term was negative, a line would look like that. If the leading term was negative for a quadratic, it would look like that. For a third degree, you'd have something of that nature. Fourth degree, something like that. And fifth degree, something like that. If you want to draw that, that's fine. I know you probably don't have different colors. Some of you guys do. You bring pencils and stuff. That's great. If you don't have it, that's all right. So now let's consider the negative ones. And let's look at, so we'll do the first degree one this time, as Carissa brought up. As x goes towards negative infinity, what happens to the y value? It goes towards positive infinity. As x goes towards positive infinity, y goes towards Let's look at an even one. Let's look at the second degree, the quadratic. As x goes towards negative infinity, y goes towards and as x goes towards positive infinity, y goes towards Why did we fill that out? Number one, there's going to be a time where you're going to need to express that, write that down. That's terminology. You'll build off of this big time in calculus. Okay? You're going to see this a lot in calculus. You're not going to see it a whole lot right now, but number one, that's notation that your books use, and we just wanted to analytically think about this. But here's the most important part that we just filled out. Watch. All the blue graphs end which direction? All the blue graphs end positive. It ends up, ends up, ends up, ends up, ends up. All of the red graphs end down. Now, do you see that all the do you see that all the evens, they start and end in the same area, don't they? If they start up, they finish up. If they start down, they finish down. All the odd ones, they switch. Okay? And that's probably the most important thing that you can think of today as we prepare for later on. Last thing we're going to do is we're going to look at single, double, and triple roots. Okay? So when we graph these, some of the interesting behavior, we have the end behavior. What it does is it goes on forever. But we also have this intermediate behavior, sometimes hidden behavior, and we look at single, double, and triple roots. And a single root looks like this. it just passes right through the x-axis. A double root touches tangent on the x-axis. And a triple root flattens out on the x-axis and then passes through. And so now we'll tie it all together. We'll tie in the graph, we'll tie in the roots, we'll tie in the end behavior. I'm going to point to a root, and you tell me whether it's a single, double, or triple. Triple. Can anybody tell me what degree polynomial is that? Is it x to the first, x to the second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th? I'll show you. If this crosses at -2, would everybody agree that x plus 2 is one of the solutions? That we would, you plug in -2, you get 0 there. And since it's a triple root, it's to the third power. This spot right here crosses through +1, and it's a double root, so it's squared. This passes through 4, and it's a single root, so it's the first power. This passes through 7, so I have x minus 7 triple root, so it's the third power. So this is x to the third, x squared, x to the third, multiply them out, and you get an x to the 9th. Now here's the cool thing. You see this polynomial, you're like, wow, that's just about impossible to graph. But that's a really complicated polynomial to come up with. I just wrote the equation for it right now. Just like that. And the really cool thing is I can then type that into my calculator. So what I did last hour, I just typed it all in just exactly like I have it. And then I adjusted my window so that 40,000 was at the top, negative 50,000 was at the bottom, 8, 2, -4. And when I press graph, I want you to actually see it. Hey, stop! There it goes. Same graph, isn't it? And we did that very, very quickly, didn't we? So we looked at a graph, we pulled off the equation. What you're going to do on Monday, if you look at this sheet right here, I have all the equations already in factored form. We're going to graph them based off their factored form. And we'll be able to do it very quickly based off our knowledge of the behavior and the single, the double, and the triple roots. You like that scene, don't you? Yeah. You want to write that one down and try it again at home, don't you? All right. Go see Footloose. That's all I have for you today.